In previous lessons, we've talked about the equations of lines, okay? We are now going to be taking a look at, because we're in 3D, the equations of a plane, okay? We've looked at very briefly, the major planes, right? The XY, the XZ, and the YZ planes, okay? The major ones. We're going to take a look at any of them now, all right? So here's what we're going to set up with. Take a look at the diagram that we have. All right. We're going to start off with a couple of conditions. First of all, the plane itself will have a point on it, and it will be the point A. All right. Now, I'm not going to mess up the diagram itself here, but we'll say A. We'll write it here. Again, is A1, A2, A3. Okay. We know this point, just like we did with this line before. Okay. Now, the other things that we have with the plane is that we're going to have two non-collinear vectors. Okay, a u, and we'll throw up another one, and we'll say v. Non-collinear, non-zero vectors. All right. One of the things that we have already looked at in the past is that any two non-collinear, non-zero vectors can span the whole plane. What that means is they can come up with another vector on the plane itself, be a linear combination of this vector. So let's say, for example, we have a point P, all right, and P is any point that's on the plane itself, okay? Any point that's on the plane. This is what we're trying to find, right? We want that P, just like we did for the lines. We wanted the point, any point that was on the line. Now we want any point that's on the plane itself, okay? So here's how we're going to start off with that. We're, again, going to start at the origin, all right? And we're going to have a vector from O to P, okay? Now, assuming this comes underneath, right? Actually, let's see if I can draw that so that it looks like it's actually coming from underneath here. We have our solid line that goes up until we see the plane, and then a dashed line to pretend that it's coming underneath, right? All right, and that's what we have there. We know that we've got the vector O to A, and we'll do the same type of thing. We'll go from O, and then when we hit underneath it, we'll dash line it through O to A there. All right, and then just like we did with the line, but this case we're going to be doing with the plane, AP, which is on the plane itself, so we'll do a solid line, is right there. Okay, so what we have, what we've developed here, if you can see, is the triangle law of addition, right? The vector addition. So we have OP, the vector OP is equal to the vector OA. Oh, I didn't need that there yet. Is the vector OA plus the vector AP. That's just vector addition right there. Nothing new there. Well, again, we've got these vectors u and v that are on the plane, and so u and v are going to act like two direction vectors. We know that there's a linear combination of u and v that come up with a and p. So we rearrange, or we substitute the vector AP with some scalar of, let's say, u plus some scalar of v, okay? And they act as our direction vectors, okay? So we actually can have two direction vectors, and when we have the second direction vector, we end up with a plane instead of just a line, okay? We have to have those two, all right? I'm going to put it here, and we're going to just say, note u and v are direction vectors of the plane. Okay, that's where that comes up with. All right. Now, if we were to substitute in the values, for the direction vectors themselves. Now, here's what we're going to say. I'll just take a little note here. All right. This equation defines the whole plane. Why? Because we can get any point that's on the plane. Remember, the head of OP is the point that we're looking for, and it is defined to be any point that's on the plane. So we get all points that are on the plane there. Okay, this is the vector equation of a plane, similar to the line, the vector equation of a plane. All right. If we were to further on and go into what is the parametric equations of the plane, well, then we'd have to convert the vectors into their component form, right? The algebraic vectors. And so that we would have x, y, z is equal to a1, a2, a3 plus the parameter s times whatever the direction vector is, u1, u2, u3 plus the parameter t with the direction vector v1, v2, v3. Okay, that's the long or the expanded form version of the vector equation of a plane. Well, the parametric equations, again, we have 3 of them. They also have an extra term to them, right? The TV1. We have y equaling a2 plus s u2 plus t v2, and z a3 plus s u3 plus t v3, right? We do not go into symmetric equations of a vector, and the reason for that is because there are 2 parameters. We'd have to choose which one we're going to use. It just becomes more complicated, so there is really no symmetric. We don't talk about a symmetric equation, okay, for the planes. So here's an example of what we can do. Now, if we're given, I'll just say this. What we want to do is determine the equation of a plane that contains, we'll say the point 1, 2, 3, B, 4, -5, 2, and C, 8, 6, -1. Okay? See, what we're going to show here too is the understanding that we have any 3 points, right? So long as they're non-collinear, they'll form a plane, right? If we think about it, 3 points, if they're collinear, right, you're just going to get a line. But 3 points that are non-collinear, you've got this triangle which extends out into the actual plane. Okay, so what we need to do is find our direction vectors, all right, find 2 non-collinear, non-zero vectors between A, B, and C, all right, so 2 non-collinear vectors. So let's say we've got our M1, our direction vector 1, we can call that AB. So we end up with 4 minus 1, -5 minus 2, and 2 minus 3. So that is 3, -7, -1. We have a second direction vector. we can say, now it's a direction vector. It doesn't have to be tail to tail in this case, okay? We just non-collinear. So what we'll say is, we'll call this one BC. We'll just go across, BC. So from there we have 8 minus 4, we have 6 minus -5, and we have -1 minus 2. So we have 4, 11, -3 as our second direction vector. You can see that these are not scalar multiples of each other, so they work. Okay? Now we've got 3 points with 2 direction vectors. We can come up with any equation or a variety of different equations. We can use the point A or B or C and use them as the position vectors OA or OB or OC. Okay, let's just say we're going to use C, so we say it's the vector 8, 6, -1 plus our first parameter with our first direction vector plus our second parameter with our second direction vector. Okay, if we wanted to use the parametric equations or use the parametric equations, right, the x, y, and z, 8 plus 3s plus 4t, 6 minus 7s plus 11t, -1 minus s minus 3t. So we have our vector equation and we have our parametric equations from there. Okay, it's tougher for me to mark whether you're getting it right or wrong because there's a number of ways to come up with this direction vector, or sorry, these direction vectors, and to come up with the final plane itself, the equation of the plane. But that's up to me. So long as you guys are finding 2 good direction vectors, non-collinear, you're using any one of these 3 points, okay, in your final, then you're getting it right there. Okay, so what's the final thing here? How do we determine if a point lies on a plane using the vector or parametric equations? Okay, well, obviously I know that you would come up with the point satisfies the equations. What does that look like, right, to satisfy the equations? Well, again, there's a bunch of algebra involved in here. If I took a look at these equations here and just said, all right, let's look at the parametric equations, and said, all right, is the point 4, 9, -7 on this plane? Okay, how would you show if it's on the plane itself? Well, remember, the equations need to be satisfied by the point. The point, if it's on the plane, needs to satisfy the equations. So that means that 4 would equal 8 plus 3s plus 4t. That 9 would equal 6 minus 7s plus 11t. And that -7 needs to be equal to -1 minus s minus 3t. Look what you have. You have 3 equations with 2 unknowns here. How do we solve? Take any 2 of these, solve for 2, check with the third. Okay, a lot of algebra. We're doing a lot of substitution elimination in this work, aren't we? Okay, and that's the idea that you can do. All right, so give your hand a try at these, work through them, get to understand planes, and the next lesson we'll take a look at another equation of a plane. Good luck.